Welcome to our review on radiation and temperature. So hopefully you remember from our earlier physics work that all objects emit electromagnetic radiation. So when you've got any warm object, it's going to emit infrared radiation, and we can actually detect the infrared radiation using a thermal imaging camera. And there's an image of a thermal imaging camera from the left there, and you can see that what we get there are the hotter parts are in the red, whereas the cooler parts tend to be the blues. Now, the type of radiation that's emitted will depend on the temperature of the object. So in the bottom right, you can see a bit of metal that's been heated up to incredibly high temperatures. So the hottest part of it is on the far right there, where you can see it's that kind of white colour. So bluish white is always the hottest. And then as we move further towards the left of that picture, you can see it goes to a yellow, which is the next hottest part. And then finally the red, which is actually the cooler part. So if we've got a hotter object, it's actually going to be emitting more radiation of a higher frequency and shorter wavelength, and less radiation of a lower frequency and longer wavelength. And if you have a look at the diagram on the left there, we've got our visible light spectrum there, ultraviolet to the right of that, infrared to the left, just as you'd expect from the EM spectrum. And what we've got are three different objects, so you can see the wavelengths and the frequencies therefore of the light that they're emitting. So the white hot object at the bottom, you can see there, that's going to be emitting more radiation with that higher frequency and shorter wavelength, because the bar extends to the right hand side and the ultraviolet side. Whereas just the warm object is on the far left of the chart there, because it's got more radiation of a lower frequency and longer wavelength than the higher frequency, shorter wavelength. Now, this is important to us because, as you know, we can't very well just go up to the various stars in the sky and take a few measurements. So what we have to do is rely on things we can measure from here on Earth or from satellites. And one of the key things we use is the light that comes from all those different stars. So we can analyse the light from the stars, and then we can plot these graphs of intensity against our frequency. And you can see one on the right hand side there. So on the y-axis we've got the intensity of the radiation at each frequency, and along the x-axis we've got the actual frequency. Just look carefully though, because you can see that it's increasing towards the left, okay, so the opposite of how we'd normally draw a graph. Now what we can see there is that when we've plotted that graph, we can spot the hottest star there with that purple line, because it's got a higher frequency and higher intensity. Whereas the coolest star, which is the red line there at the bottom, that's only got a very low amount of our high frequency waves. So we need to know about the link between temperature and radiation. So if we've got an object which is emitting the same amount of radiation as it's absorbing, then the temperature of that object will remain constant. If, however, it's unbalanced in one way, the temperature will change. So if we're actually emitting more radiation than we're absorbing, then that means the object is going to cool down. Whereas if more radiation is being absorbed than is emitted, then the temperature of the object will increase. So if we now consider this in terms of the Earth, what we actually have there is the reason our planet has the temperature that allows life to exist is because we're absorbing radiation from the sun. Now, at the same time that we absorb radiation from the sun, then the Earth will also emit some radiation back into space. So what we find is that we should have a certain amount of that radiation being reflected back into space from the Earth itself. However, as we've looked at in our chemistry work, we know that certain human interactions are leading to increased amounts of greenhouse gases, so carbon dioxide, water vapour, methane. And as a result of this, what we're actually finding is the concentration of the greenhouse gases in the atmosphere is increasing. Now, if we've got a higher concentration of our greenhouse gases in the atmosphere, then they're actually going to absorb the infrared radiation that should be emitted back into space, and then reflect that back to the Earth's surface. So what we find is, in theory, the Earth should have a very constant temperature, because we get the radiation from the sun, which is absorbed by the Earth, and then we emit radiation back into space which passes through the atmosphere. However, if the amount of greenhouse gases changes, that could lead to changing temperatures on the Earth as well. Hopefully at the end of this review you can now explain how the intensity and wavelength distribution of radiation emitted by an object depends on its temperature. You can explain the relationship between the temperature of an object and the radiation that it emits and absorbs, and you can explain why the temperature of the Earth or other objects does or does not change using that knowledge.